The surface of the sun reaches temperatures of nearly 10,000 degrees Fahrenheit. That is the temperature of the surface, the part you can see. The corona, the wispy outer atmosphere that extends millions of miles into space, burns at over 3 million degrees Fahrenheit. Scientists have known this for decades, and for decades not one of them could fully explain why. Heat flows from hot to cold. Every child learns this. Every law of thermodynamics confirms it. So why does the sun's outer atmosphere get hotter the farther it stretches from the nuclear furnace below? It defies the most fundamental rules of how energy behaves. It is, even today, one of the most stubborn, unsolved mysteries in solar physics. And then, in the summer of 2018, NASA launched a spacecraft the size of a small car directly toward the sun. Not toward the sun in the way a probe might swing past it during a gravity assist maneuver. Not a safe, distant observation run from the comfortable darkness of deep space. Toward the sun, into its atmosphere, into the corona itself, into the region where the rules of physics seem to break down and no instrument had ever survived long enough to take a measurement worth trusting. The Parker Solar Probe flew closer to the sun than any human-made object in history. It reached a closest approach distance of roughly 4 million miles from the solar surface, a number that sounds enormous until you consider that Earth sits approximately 93 million miles away. The probe traveled inside the orbit of Mercury, into a region of space so saturated with solar radiation that conventional spacecraft design would have been instantly fatal to every instrument on board. And it did not fail. It did not melt. It did not go dark. It sent back data of a quality and precision that the scientific community had never possessed before. How? The answer is not magic. It is not luck. It is one of the most elegant feats of thermal engineering ever conceived. And understanding it requires first understanding exactly what the sun is, what the corona actually does, and why reaching it was considered impossible for so long. The sun is not burning in the way a campfire burns. That distinction is worth sitting with for a moment. A campfire is a chemical reaction, carbon molecules combining with oxygen to release energy as heat and light. The sun operates on a mechanism so much more violent, so much more fundamental to the architecture of matter itself, that comparing the two is almost meaningless. At the core of the sun, gravity compresses hydrogen gas to densities and temperatures that our instruments can only infer, never directly measure. The temperature at the solar core reaches approximately 27 million degrees Fahrenheit. Under those conditions, hydrogen nuclei, bare protons stripped of their electrons, are forced close enough together that the strong nuclear force takes over. Protons fuse. Helium is born. And in that transformation, a tiny fraction of mass converts directly into energy according to a relationship that Albert Einstein described in 1905. Energy equals mass times the speed of light squared. The speed of light is approximately 186,000 miles per second. Square that number, then multiply it by even a small amount of mass. The energy released is extraordinary. Every second, the sun converts approximately 600 million metric tons of hydrogen into 596 million metric tons of helium. The missing 4 million metric tons become pure energy, radiated outward as photons, neutrinos, heat, and light. That energy does not travel instantly from the core to the surface. A single photon produced in the solar core can take anywhere from 10,000 to 170,000 years to finally escape. Not because the distance is so vast, but because the sun's interior is so dense that the photon is absorbed and re-emitted billions of times before it finds a path to the surface. Once it reaches the outer layers and escapes, it crosses the 93 million miles between the sun and Earth in just 8 minutes and 20 seconds. That contrast alone, thousands of years inside, 8 minutes across open space, begins to reveal how extreme the sun's internal environment truly is. The visible surface of the sun, what astronomers call the photosphere, is not a solid surface in any conventional sense. It is the point at which the solar plasma becomes thin enough to be transparent, the level from which light finally escapes into space without being immediately reabsorbed. It seethes. It churns. Giant convection cells called granules, each roughly 1,000 miles across, rise and fall continuously, carrying heat from the layers below and releasing it at the surface. At any given moment, the photosphere hosts hundreds of thousands of these structures simultaneously. Beyond the photosphere lies the chromosphere, a reddish layer extending roughly 2,000 miles outward. Then comes the corona, the sun's outer atmosphere, stretching millions of miles into space and ultimately merging into the solar wind that flows past every planet in the solar system, including Earth. The corona is invisible to the naked eye under ordinary circumstances. The photosphere is so much brighter that the corona is completely washed out. The only time it becomes visible without instruments is during a total solar eclipse, when the moon blocks the photosphere precisely enough to let the corona glow faintly in the darkened sky. A white structured halo of plasma that ancient observers found beautiful and terrifying in equal measure. When scientists first measured the temperature of the corona in the 1940s, they expected to find temperatures somewhat lower than the photosphere. Cooler as the distance from the energy source increased, exactly as physics would demand. What they found instead stopped the field cold. The corona was not cooler, it was hotter, dramatically, inexplicably hotter. The photosphere burns at roughly 10,000 degrees Fahrenheit. The corona burns at 1 to 3 million degrees. Some localized regions in the corona reach temperatures of 10 million degrees or more. This became known as the coronal heating problem. It remains one of the central unsolved questions in astrophysics. Dozens of mechanisms have been proposed over the decades: alpha wave dissipation, nanoflare heating, magnetic reconnection events. Each hypothesis has evidence supporting it. None has been definitively confirmed. And until a spacecraft could actually enter the corona and measure what is happening from the inside, any conclusion remained theoretical. For most of the 20th century, entering the corona was not simply dangerous. It was considered impossible by engineering standards. The sun emits not just heat and light, but a constant stream of charged particles, the solar wind, and periodic explosions of plasma and magnetic field called coronal mass ejections. A single coronal mass ejection can carry billions of tons of plasma traveling at speeds between 200 and 2,000 kilometers per second. When these events strike Earth's magnetic field, they produce geomagnetic storms capable of disrupting power grids, disabling satellites, and lighting up auroras at latitudes where they are rarely seen. Now consider placing a spacecraft inside the corona, inside the source of those ejections, inside the region where the magnetic field is most chaotic and the particle densities are highest, and keeping its instruments alive, calibrated, and communicating with Earth. The thermal challenge alone is staggering. At Parker's closest approaches, the spacecraft faces solar irradiance approximately 500 times more intense than what Earth-orbiting satellites experience. The heat shield faces temperatures exceeding 2,500 degrees Fahrenheit. Yet the instruments behind the shield must be kept near room temperature, within a range of roughly 80 degrees Fahrenheit, or they simply stop working. Getting a spacecraft to the sun is also, paradoxically, one of the most difficult navigation challenges in the solar system. Earth orbits the sun at approximately 67,000 miles per hour. A spacecraft launched from Earth carries all of that orbital velocity with it. To fall inward toward the sun, a probe must slow down relative to the sun. It must cancel out that enormous inherited velocity. The fuel required to do this directly would be prohibitive. Even the heaviest rockets ever built could not carry enough propellant to send a meaningful science payload directly into a solar orbit this close. The solution engineers devised over decades of planning required a completely different approach, and it relied on a planet most people rarely think of when imagining space exploration. That planet is Venus. The Parker Solar Probe did not fly straight to the sun. Over the course of its 7-year primary mission, it used Venus as a gravitational brake, performing a series of 7 Venus flyby maneuvers, each one carefully timed to bleed off orbital velocity and reshape the probe's trajectory into an increasingly elongated ellipse diving closer and closer to the solar surface with every orbit completed. 7 encounters with Venus, 24 orbits around the sun, each perihelion, each closest approach, pushing deeper into the corona than the last. The probe was named after Eugene Parker, a theoretical astrophysicist at the University of Chicago, who in 1958 proposed the existence of the solar wind, the continuous stream of charged particles flowing outward from the sun in all directions. His paper was initially rejected by reviewers who called the idea implausible. It was published only after the intervention of another physicist who recognized its validity. Less than 3 years later, the Mariner 2 spacecraft confirmed Parker's prediction with direct measurements. He lived to see his name placed on the spacecraft that would finally enter the environment he had predicted 6 decades earlier. Eugene Parker died in March of 2022 at the age of 94. By that point, the probe bearing his name had already completed multiple close passes of the sun, transmitting data that confirmed and complicated theories he had spent a lifetime building. The science was working. The spacecraft was surviving. And what it was finding inside the corona was stranger than almost anyone had predicted. 60 years of solar physics built its understanding of the solar wind on a single, unavoidable limitation. Every measurement ever taken was taken from a distance. Earth-based observatories, space telescopes, even the most capable instruments mounted on satellites in Earth orbit, all of them read the solar wind as it arrived, already aged, already modified by millions of miles of travel. What scientists were studying was not the solar wind, it was the solar wind's aftermath. The difference matters enormously. When a forensic investigator studies a crime scene, the freshness of the evidence determines the quality of the conclusions. Evidence collected the same hour tells a different story than evidence collected 3 weeks later, after rain and wind and foot traffic have rearranged everything. Solar physics, for most of its history, was working from 3-week-old evidence. The solar wind that strikes Earth's magnetosphere has traveled approximately 93 million miles since it left the sun. In that journey, it has expanded, cooled, mixed with older plasma streams, been compressed by shock waves from other eruptions, and interacted with the magnetic fields of multiple planets. By the time it reaches our instruments, it is not the solar wind. It is a shadow of it. This was the core scientific justification for the Parker Solar Probe's design and trajectory. Not spectacle, not records. The probe needed to sample the solar wind at its source, or as close to its source as engineering could achieve, before the outflowing plasma had time to erase its own fingerprints. The solar wind itself requires some unpacking. It is not a wind in any atmospheric sense. There are no molecules, no nitrogen, no oxygen, no weather systems in the familiar meaning of the word. The solar wind is a continuous outflow of ionized particles, mostly protons and electrons with a smaller fraction of helium nuclei, that escapes the sun's corona at speeds ranging from roughly 250 miles per second in its slower streams to over 500 miles per second in its fast streams. On occasion, during the most violent solar eruptions, localized flows can exceed 1,000 miles per second. To give that a terrestrial reference point, the fastest wind ever recorded on Earth's surface reached approximately 231 miles per hour during Tropical Cyclone Olivia in 1996. The slow solar wind moves at roughly 900,000 miles per hour. The fast solar wind moves at approximately 2 million miles per hour. These are not gusts. These are not transient events. This is the sun's permanent, ceaseless exhalation, blowing outward in all directions, every second of every day, filling the entire volume of the solar system out to a boundary called the heliopause, roughly 11 billion miles from the sun. Every planet is immersed in this flow. Every comet's tail points away from the sun, not because of the direction of travel, but because the solar wind physically pushes the ions in the coma away from the sun, regardless of which direction the comet is moving. Earth's magnetic field deflects most of this particle stream around the planet, compressing on the sunward side and stretching into a long teardrop shape on the night side. Without that magnetic shield, the solar wind would have stripped away Earth's atmosphere over billions of years, the way it appears to have stripped the atmosphere from Mars after Mars lost its global magnetic field sometime in the first billion years of solar system history. The solar wind is not a background feature of the solar system. It is one of the most consequential ongoing physical processes within it. And yet its origin, specifically the mechanism by which the corona's plasma overcomes the sun's gravitational pull and accelerates to these extraordinary velocities, remained poorly constrained well into the 21st century. Eugene Parker's original 1958 model predicted that the solar wind must exist because the corona is so hot that its outer layers cannot be gravitationally bound to the sun. The thermal pressure of the plasma overcomes gravity at a certain distance, and from that point outward, the material simply flows away. Parker was correct in the broad strokes. What he could not predict in detail, because no data existed to constrain the models, was the precise structure of the solar wind close to its source. Two fundamental types of solar wind had been identified by decades of spacecraft measurements taken further from the sun. The fast solar wind, blowing at speeds above approximately 400 miles per second, originates from structures called coronal holes, regions where the sun's magnetic field opens outward into space rather than looping back to the solar surface. In coronal holes, plasma can escape along these open field lines without obstruction. The slow solar wind, moving at speeds below roughly 300 miles per second, is messier. Its origin was genuinely contested for decades. It appeared to come from the edges of closed magnetic regions, from the equatorial belt of the sun, from boundaries between different magnetic structures, but the exact mechanism by which it was released and accelerated was not agreed upon. The Parker Solar Probe's instruments were designed specifically to resolve this ambiguity, and almost immediately they began delivering surprises. During the probe's very first close passes of the sun in late 2018 and early 2019, the Fields instrument, a suite of antennas and magnetometers designed to measure electric and magnetic fields in the surrounding plasma, began detecting something nobody had predicted with this frequency or this intensity. The sun's magnetic field, which was expected to be relatively ordered close to the solar surface before the solar wind had time to tangle it, was instead full of violent, rapid reversals. The magnetic field would be pointing outward from the sun, flowing normally. Then, over a period of seconds to minutes, it would flip by 180 degrees, pointing back toward the sun, before flipping outward again. These reversals were not gradual. They were abrupt, structured, and accompanied by sharp spikes in plasma velocity. Where the magnetic field reversed, the solar wind suddenly accelerated. The plasma jets associated with these reversals were moving significantly faster than the surrounding wind. Scientists named these structures switchbacks. The term captures their geometry precisely. Imagine a river flowing downstream, and then picture a section of the current that abruptly curls back upstream, doubles over itself in a tight S shape, and then resumes its downstream course. The water in that S-shaped section is moving backward relative to the overall flow, while the current on either side continues forward. The switchbacks in the solar magnetic field behave analogously. Localized reversals, brief in duration, embedded in the larger outward-flowing structure of the solar wind. What made switchbacks immediately significant was the energy packed inside them. When a magnetic field line bends sharply, it stores tension, in exactly the same way a bent steel rod stores mechanical stress. When the field straightens, that tension releases. The energy has to go somewhere. In a plasma, it converts into heat and kinetic energy of the particles. Scientists looked at the magnitude of these reversals and the frequency with which they appeared near the sun, and the numbers were large enough to make a testable claim. Switchbacks, if they originated inside the corona, might be carrying enough energy to contribute substantially to coronal heating. Justin Casper, principal investigator for the SWEEP instrument suite at the University of Michigan, described the discovery in direct terms. His team had expected to find waves closer to the sun, but what they found instead were coherent, structured velocity spikes, not random turbulence, but organized events. The solar wind, viewed from this proximity, was not the smooth, uniform outflow that distant measurements had suggested. It was violent, structured, and far more dynamic than any model had captured. 4 papers were published simultaneously in the journal Nature in December of 2019, reporting the first science results from Parker's initial close passes. The papers covered the magnetic field measurements, the particle environment, the solar wind structure, and the imaging of coronal features. Together, they delivered a consistent message. The inner heliosphere, the region of space close to the sun that no spacecraft had ever sampled before, was physically different from what the models said it should be. The solar wind was rotating faster than predicted. The probe's instruments detected a surprisingly large azimuthal velocity component, meaning the plasma was not just flowing radially outward from the sun, but also swinging sideways in the direction of the sun's rotation, with far greater force than models had calculated. This had implications for how the sun loses angular momentum over time, a process that has been gradually slowing the sun's rotation over its 4.5 billion year history. The dust environment near the sun was also different. Scientists had long predicted the existence of a dust-free zone close to the sun, where the solar radiation would be intense enough to vaporize interplanetary dust particles before they could accumulate. Parker's data suggested this zone began at a closer distance than models had placed it, but also that the inner solar system was not as dust-depleted as some theories required. These were not minor adjustments to existing models. Each discrepancy pointed to a gap between what physics predicted and what the sun actually does. Gaps of that kind, in science, are not problems. They are the locations where new understanding lives. The switchback mystery, however, proved more resistant than initial excitement suggested. By the mid-2020s, after Parker had completed more than a dozen close orbits, the question of where switchbacks originate had not been resolved, but it had been narrowed in a way that was itself revealing. A research team at the University of Michigan, analyzing data from Parker's first 14 close passes, searched specifically for switchbacks inside the corona. In the region the probe had actually penetrated, the S-shaped magnetic reversals, so abundant in the near-sun solar wind just outside the corona, were essentially absent inside it. This was a negative result, and negative results in physics carry precisely as much information as positive ones. If switchbacks were absent inside the corona, they were not forming at the solar surface and propagating outward through the corona into the solar wind. That ruled out one of the two leading formation hypotheses. The remaining hypothesis, that switchbacks form in the solar wind itself, triggered by some mechanism that originates lower down but manifests higher up, became the more likely candidate. But the data to confirm it conclusively did not yet exist. Parker's closest approaches, still ahead of it in the mission timeline, would need to go deeper. And on December 24, 2024, the probe did exactly that, flying to within 6.1 million kilometers of the solar surface, the closest any human-made object had ever come to a star. What its instruments recorded during those hours inside the corona would take weeks to fully transmit back to Earth and months to analyze. The answers were in the data. Scientists just had to read them carefully enough. The heat shield on the Parker Solar Probe is 4.5 inches thick. That is approximately the width of a human hand, palm to fingertip. Behind it, a suite of instruments worth hundreds of millions of dollars operates at temperatures close to room temperature, while the shield's front face absorbs radiant energy, intense enough to melt aluminum within seconds. The margin between survival and destruction is not measured in large engineering tolerances. It is measured in the precision of a shadow. Everything the probe can do scientifically, every measurement, every magnetic field reading, every particle count, depends on that shadow holding. The shield must face the sun within a tolerance of 1 degree. If the spacecraft drifts far enough that even a small portion of the instrument payload emerges from the shadow and catches direct sunlight at this distance, the thermal load on the exposed component increases by a factor large enough to cause immediate damage. The probe's attitude control system, a set of reaction wheels and hydrazine thrusters, monitors orientation continuously and corrects it autonomously. At the distances of closest approach, the communication delay between the probe and Earth is measured in minutes. No human operator could intervene fast enough to save it. The spacecraft makes those decisions alone. This is not a minor operational detail. It defines the entire mission architecture. Every science instrument, every antenna pointing strategy, every data downlink schedule was designed around a single non-negotiable constraint. The shield stays between the probe and the sun, always, without exception. The material chosen for the shield is a carbon composite foam sandwiched between two carbon fiber facesheets. Carbon was selected for a combination of properties that no metal or ceramic could simultaneously provide. It is light, a critical constraint for a spacecraft whose launch mass and trajectory were carefully calculated. It has an extraordinarily high melting point, above 6,500 degrees Fahrenheit, Far above the approximately 2,500-degree temperatures, the shield's sunward face reaches at closest approach. It has low thermal conductivity, meaning heat absorbed at the front face does not transfer efficiently to the rear face where the instruments sit. And it has low thermal expansion, meaning the shield does not warp or change shape significantly as its temperature rises and falls during each orbit. The front face of the shield is coated with a white alumina-based paint. White, in the context of solar radiation, reflects visible light. The more visible light reflected, the less energy absorbed as heat. The coating was engineered to have high reflectivity across the solar spectrum while maintaining high emissivity in the infrared, meaning the shield re-radiates as much absorbed energy as possible back into space as thermal infrared emission rather than conducting it inward. This balance between absorption, reflection, and re-radiation is what keeps the rear face of the shield and the instruments behind it at temperatures the electronics can tolerate. The engineering is elegant in the way the best engineering always is. It does not fight the environment. It routes the energy around the thing that needs to survive. Getting the probe to the sun required solving a problem that had blocked solar close-approach missions for decades. The difficulty is counterintuitive. Reaching the inner solar system, flying closer to the sun than any previous spacecraft, requires slowing down, not speeding up. This seems backward. Objects fall toward gravitational sources when they lose energy. To fall toward the sun, a spacecraft must lose kinetic energy relative to the sun, but it starts its journey from Earth, which is orbiting the sun at approximately 67,000 miles per hour. The spacecraft inherits every bit of that velocity at the moment of launch. To reach a very close solar orbit directly, the probe would need to cancel most of that inherited velocity. The delta V, the change in velocity, required to do this directly would demand a quantity of propellant that no rocket currently flying could lift alongside a meaningful science payload. The numbers simply do not close. The solution developed over years of mission planning relied on orbital mechanics rather than propulsion. Specifically, it relied on using Venus as a gravitational brake in a maneuver called a gravity assist, sometimes called a slingshot, though in this case the intent was to lose energy rather than gain it. A gravity assist works by flying a spacecraft through the gravitational field of a planet in a precisely calculated trajectory. If the spacecraft approaches the planet from behind, in the direction of the planet's orbital motion, it gains energy from the planet's gravity and accelerates. This is how the Voyager probes used Jupiter and Saturn to reach the outer solar system. If the spacecraft approaches from the front, flying against the planet's direction of motion, it transfers energy to the planet and decelerates. The energy exchange is real. The planet's orbit changes by an infinitesimally small amount, and the spacecraft's orbit changes by a measurable, mission-enabling amount. Parker used Venus as this gravitational drain 7 times over the course of its primary mission. Each Venus flyby was carefully timed and aimed to extract a specific amount of orbital energy, reshaping the probe's elliptical orbit around the Sun into one with a progressively smaller perihelion, the closest point of approach. Between flybys, the probe completed full solar orbits, collecting data at each perihelion before swinging back out, adjusting course at Venus, and diving inward again on the next pass. The first perihelion, in November of 2018, brought the probe to approximately 15 million miles from the solar surface, already closer than any previous spacecraft. By the end of the mission's primary phase, that number had been reduced to approximately 3.8 million miles. The orbital period at that distance is only about 88 days, meaning the probe completes a full orbit around the Sun faster than Mercury does. Inside the corona, the physical environment is unlike anything else in the solar system. The plasma there is tenuous by laboratory standards. The particle density is far lower than what most people would consider a vacuum on Earth, but the energy per particle is enormous. The corona's temperature, in the range of 1 to 3 million degrees Fahrenheit and higher in some active regions, does not mean the probe's instruments are bathed in scorching heat in the conventional sense. Temperature in a plasma is a measure of the kinetic energy of individual particles. In the corona, those particles are moving extremely fast, but they are also extremely sparse. The actual energy transferred to a physical object by particle collisions in the corona is relatively small compared to the radiant energy transferred by photons arriving directly from the photosphere. This distinction between particle temperature and radiant heat flux is precisely why the probe can survive inside a plasma of millions of degrees while being primarily protected against a heat load of approximately 2,500 degrees Fahrenheit. The corona is incomprehensibly hot at the atomic level, but it is thin enough that the probe's heat shield can manage the energy budget. Think of it in terrestrial terms. A spark flying from a grinding wheel reaches temperatures of several thousand degrees Fahrenheit at the surface of the glowing metal fragment. If that spark touches your skin for a fraction of a second, you may feel nothing at all. The temperature of the spark is enormous. The total thermal energy it carries is negligible because its mass is so small. The corona operates on a similar principle at a vastly larger scale. Its individual particles are extraordinarily energetic. Its total energy content per unit volume, relative to the energy arriving as photons from the photosphere below, is manageable. This is not accidental. It is a direct consequence of the coronal heating problem. The corona is hot because something is preferentially heating its particles, not because the photosphere below is radiating that energy upward efficiently. If the corona were hot because the photosphere was heating it conductively from below, the radiant energy flux inside the corona would be proportionally higher, and survival at these distances would be physically impossible for any foreseeable spacecraft design. The 4 instrument suites aboard the Parker Solar Probe were designed to measure 4 distinct aspects of the near-Sun environment simultaneously, so that correlations between different physical quantities could be established rather than inferred. The Fields Instrument Suite measures electric and magnetic fields, radio waves, and plasma waves. Its sensors include fluxgate magnetometers, a search coil magnetometer, and electric field antennas that extend outward from the spacecraft body, deployed into the sunward hemisphere, directly exposed to the solar environment. The antenna booms are made from a niobium alloy that maintains its structural integrity at high temperatures. The data they collect has a time resolution fine enough to capture changes in the magnetic field on scales shorter than 1 second. The Sweep Suite, solar wind electrons, alphas, and protons, measures the velocity, density, and temperature of the solar wind's constituent particles. Its primary sensors include a Faraday cup, a simple but extraordinarily robust instrument consisting essentially of a metal cup that catches charged particles and measures the electrical current they produce as they strike its collector. The Faraday cup used on Parker is the first instrument of its kind designed to operate in direct sunlight at this proximity to the sun. It extends beyond the heat shield's shadow and directly samples the solar wind plasma. Its operating temperature reaches over 1,800 degrees Fahrenheit during the closest passes. The ISIS Suite, Integrated Science Investigation of the Sun, measures energetic particles, ions and electrons accelerated to high energies by solar flares and coronal mass ejections. These particles are the ones that pose radiation hazards to both spacecraft electronics and, in a broader context, to astronauts and infrastructure in space and on Earth during major solar events. Understanding how the sun accelerates them, the mechanism, the timing, the energy spectrum, is one of the central questions in space weather science. The Whisper Imager, Wide-Field Imager for Solar Probe, is the probe's only optical instrument. It captures images of coronal structures, solar wind density variations, and coronal mass ejections using visible light, operating in a geometry that no previous telescope had occupied. From inside the corona, the structures that ground-based coronagraphs and space telescopes observe from millions of miles away appear in completely different angular perspective, revealing 3-dimensional features that are geometrically compressed into 2 dimensions when viewed from a distance. Solar magnetic fields are the connective tissue of all these measurements. Every major process the probe was designed to study, coronal heating, solar wind acceleration, particle energization, switchback formation, involves magnetic fields either as the primary driver or as an essential mediator. Understanding what Parker was measuring requires understanding something fundamental about how magnetic fields behave in a plasma. In an ordinary gas, air for instance, magnetic fields pass through the material with relatively little interaction. The gas molecules are electrically neutral. They do not strongly couple to magnetic field lines. A plasma is different. Plasma consists of free charges. electrons and ions that are not bound to each other. Free charges moving through a magnetic field experience a force, the Lorentz force, that curves their trajectories. Conversely, when plasma moves, its free charges carry magnetic field lines along with them, deforming and stretching the field structure. Physicists describe this behavior using the concept of magnetic flux freezing or flux freezing. In a highly conductive plasma, the magnetic field and the plasma are effectively locked together, each constraining the motion of the other. In the sun's corona, this coupling between plasma and magnetic field is extraordinarily tight. The magnetic field lines emerging from the photosphere do not simply sit passively in the corona while the plasma flows around them. They are dragged, stretched, twisted, and braided by the convective motions of the plasma below. When field lines of opposite polarity are pushed close together, they can undergo a process called magnetic reconnection, snapping apart, reconfiguring, and releasing stored magnetic energy as heat and kinetic energy of the surrounding plasma. This reconnection process had been theorized for decades as a potential coronal heating mechanism. Confirming it observationally required instruments inside the corona, measuring field geometry and particle energetics simultaneously at the same location. Parker collected that data. And in August of 2025, a research team published results in a peer-reviewed journal confirming that Parker had directly observed magnetic reconnection events inside the corona at scales and frequencies consistent with theoretical models, the first direct observational confirmation of a mechanism that had been hypothesized for more than half a century. The corona was not simply hot. It was being continuously heated by a process that had left its signature in the magnetic field geometry all along. The probe had flown into the evidence, and the evidence had spoken. But the full picture was still not complete. The reconnection events Parker observed were consistent with theoretical predictions, yet the total energy budget did not fully account for the coronal temperature. Something else was also at work. Or perhaps the same mechanism was operating at scales too small for even Parker's instruments to resolve directly. The next answer was not going to come from a single measurement. It was going to come from the moment Parker's instruments caught the sun in the middle of one of its most violent acts. On September 6, 2022, the Parker Solar Probe flew directly through a coronal mass ejection, not past it, not through its outer edges, through the body of it, inside the erupting plasma cloud, sampling its magnetic field and particle environment from within the structure itself, at a distance from the sun where no spacecraft had ever operated before. The field's magnetometers recorded the field geometry in real time. The sweep instruments measured the particle velocities and densities as the eruption swept over and around the probe. The Whisper imager captured the optical structure of the event from a perspective that had never existed in the history of solar observation. The data that came back changed the field. Magnetic reconnection had been theorized as a coronal heating mechanism since the 1950s. The basic idea had been articulated clearly. When magnetic field lines of opposite polarity are pushed together by the convective motions of the solar plasma, they do not simply pass through each other. In a highly conductive plasma, field lines are frozen to the plasma, as described in Act 3. When lines of opposite polarity are forced into contact, the current sheet between them becomes unstable. The field lines break, reconnect in a new configuration, and release their stored magnetic tension as explosive jets of plasma and energetic particles. The process converts magnetic potential energy, energy stored invisibly in the geometry of the field, into kinetic energy and heat. The theory was elegant. It was mathematically consistent. It was supported by remote observations from Earth-based coronagraphs and from satellites in Earth orbit that could image reconnection signatures in the corona through ultraviolet and X-ray telescopes. But remote observation, no matter how sophisticated, cannot replace in situ measurement. Seeing reconnection from a distance is like watching a fire from across a valley and concluding it is hot. Being inside it is a different category of knowledge entirely. The September 2022 encounter gave scientists something they had not possessed before: simultaneous imaging and direct particle measurement from inside an active reconnection region in the solar corona. The field's instrument suite recorded the magnetic field reversal signatures characteristic of a current sheet. the thin boundary layer where oppositely directed field lines are pressed together. SWEEP detected the plasma jets predicted by reconnection theory, high-velocity streams of particles shooting outward from the reconnection site in both directions along the current sheet, exactly as the models said they should. The particle energies measured inside the reconnection exhaust matched the predictions of theoretical models that had been developed and refined over nearly 7 decades. Dr. Ritesh Patel of the Southwest Research Institute, who led the analysis team, described the measurements directly. The data validated numerical simulation models of magnetic reconnection that had existed since the mid-20th century, providing real high-resolution in situ constraints that no previous mission had been capable of supplying. The results were published in Nature Astronomy in August of 2025. The confirmation closed a gap that had existed since the 1950s, the gap between theory and direct physical observation. But it opened an equally important new question immediately. The reconnection events Parker observed were energetically significant. The particle acceleration they produced was measurable and substantial. The question was whether they were energetically sufficient, whether reconnection alone could account for the corona's temperature, or whether it was one contributor among several operating simultaneously. The answer that emerged from the data was one contributor among several. Reconnection was real, was operating at the scales theory predicted, and was accelerating particles to energies that mattered. But the total energy budget of the corona was not fully explained by reconnection alone. A separate and equally startling finding came from analysis of Parker's crossings of the heliospheric current sheet, a vast warped surface extending outward through the entire solar system, marking the boundary between regions of solar magnetic field pointing inward toward the sun and regions pointing outward. The heliospheric current sheet is not a sharp boundary. It is a layer, a few thousand miles thick in the inner solar system, where the field reverses direction and the solar wind structure becomes complex. Parker crossed this sheet multiple times during its close approaches, and in June of 2025, a team led by Dr. Mihir Desai of the Southwest Research Institute published an analysis of what the probe had measured during those crossings. The numbers were not what anyone expected. Inside the core of the reconnection exhaust region at the heliospheric current sheet, Parker detected trapped energetic protons carrying roughly 1,000 times more energy than the available magnetic energy per particle predicted by standard reconnection theory. 1,000 times. The magnetic energy stored in the field geometry at the reconnection site was, by the standard accounting, insufficient to accelerate particles to those energies. The particles were far more energetic than the local energy budget seemed to allow. The mechanism responsible is a process called magnetic island merging. When reconnection occurs in a large current sheet, it does not produce a single clean reconnection event. It produces multiple reconnection sites simultaneously, creating isolated loops of closed magnetic field, magnetic islands, between them. These islands, trapped between active reconnection regions, are squeezed and compressed as the reconnection regions on either side continue to operate. Particles trapped inside the islands are accelerated not just once, but repeatedly, each compression event adding energy. The cumulative effect can drive particle energies far above what a single reconnection event could produce. This was the mechanism the data pointed toward. Particles were not simply escaping from a single reconnection site. They were being recycled through a chain of successive accelerations inside a complex, dynamically evolving magnetic structure. The corona, viewed from inside, was not a passive medium through which energy slowly diffused. It was an active particle accelerator, operating through a cascade of interconnected magnetic processes distributed across an enormous volume. The switchback origin question, which had remained open since the first encounters of 2018, also reached a partial resolution through an unexpected path. By analyzing Parker's data from multiple close passes alongside complementary observations from the European Space Agency's Solar Orbiter mission, a separate spacecraft operating at somewhat greater distances from the Sun, but equipped with instruments capable of imaging the solar surface in ultraviolet wavelengths with high resolution, researchers identified a structural correspondence between switchbacks measured in the solar wind and specific magnetic features on the photosphere below. The photosphere is organized at large scales into convection cells called supergranules. structures roughly 25,000 miles across that are driven by the same convective processes that produce the smaller granules visible at finer scales. At the boundaries between supergranules, the convective flows push magnetic field concentrations together, creating regions of enhanced field strength called magnetic funnels, narrow concentrations where field lines are gathered and channeled upward into the corona above. Parker's data, when correlated with solar orbiters' surface imaging, showed that switchbacks in the solar wind were spatially and temporally aligned with these magnetic funnels. The S-shaped magnetic reversals did not form randomly throughout the corona. They formed at specific locations, rooted in the magnetic topology of the photosphere below, and were launched into the solar wind from inside the funnel structures, where the field was concentrated and the plasma velocity was enhanced. Dr. Noor Rawafi, Parker Solar Probe project scientist at the Johns Hopkins University Applied Physics Laboratory, summarized the finding precisely. The probe had established the relationship between magnetic switchbacks and the supergranule boundary structures on the solar surface, directly connecting a phenomenon observed in the solar wind to its physical origin point on the star below. This was not a minor clarification. For years, two competing hypotheses had explained switchbacks as either photospheric in origin, generated at or near the solar surface and propagating outward, or as a product of the solar wind itself, generated in the expanding plasma above the corona through velocity shear instabilities. The correlation with magnetic funnels strongly favored the photospheric origin hypothesis. Switchbacks were born at the sun's surface, inside specific magnetic structures, and carried outward through the corona by the solar wind. In December of 2024, during Parker's record closest pass at 6.1 million kilometers from the solar surface, the Whisper imager recorded something that had never been captured before and was not fully anticipated by the mission's science planning team. Images from that encounter, published in December of 2025 in the astrophysical journal Letters, revealed that during a coronal mass ejection, not all of the magnetic material ejected from the sun escaped into interplanetary space as expected. Some of it turned around. A fraction of the magnetic flux released with the ejection, the loops of field that theory said should be dragged outward by the erupting plasma cloud, instead bent back toward the sun, returning to the solar atmosphere after the ejection had passed. The Whisper images showed this U-turn clearly. Magnetic field structures rising with the coronal mass ejection, then curving back sunward, reshaping the structure of the solar atmosphere in ways that prior models had not predicted. Dr. Angelos Vorlidis, Whisper project scientist at the Johns Hopkins University Applied Physics Laboratory, stated the implication directly. The magnetic field released with a coronal mass ejection does not simply escape as expected. The returning flux changes the shape of the solar atmosphere, and that reshaped atmosphere influences the character of the next coronal mass ejection that follows from the same region. The sun, in other words, has a form of magnetic memory. Each major eruption does not simply discharge accumulated field and reset the corona to a neutral state. The field that returns modifies the environment in which the next eruption will develop. The corona after a major event is not the same corona that existed before it. The conditions that determined the previous eruption's character are not simply restored, they are altered. This finding had immediate implications for space weather forecasting. Predicting the timing, direction, and intensity of coronal mass ejections, the solar events most capable of disrupting satellites, power grids, and communication systems on Earth, requires accurate knowledge of the pre-eruption magnetic state of the corona. If that state is being continuously modified by the magnetic memory of previous eruptions in ways that ground-based models did not account for, then every forecast model built before this discovery contained a structural gap. Parker had not simply confirmed existing physics, it had identified a dynamic that existing models had missed entirely. By mid-2025, more than 700 peer-reviewed scientific papers had been published using data from Parker's first 4 years of operation alone. Each orbit added new data. Each new data set revealed new structure in what had previously looked like simpler systems. The corona was not a region of uniform hot plasma gradually releasing its energy into the solar wind. It was a structured, layered, dynamically active environment where magnetic energy was being built, stored, and released through multiple simultaneous mechanisms operating at different spatial scales and time scales, from the microscopic reconnection events at current sheet boundaries to the vast months-long reorganizations of global magnetic topology following major eruptions. The probe that was not supposed to survive was not only surviving, it was rewriting the textbook on solar physics, one orbit at a time. And through all of it, through the switchbacks and the reconnection jets and the magnetic U-turns, one question remained at the core of everything. The coronal heating problem, the question Eugene Parker spent his career building theoretical frameworks to address, the question that motivated the probe's design and trajectory and the extraordinary thermal engineering challenge of its heat shield, that question had not been definitively answered. It had been narrowed. It had been sharpened. The energy budget was better constrained. The mechanisms were better characterized. But the precise partition of heating between wave dissipation, reconnection, nanoflares, and other processes remained an active area of research with competing hypotheses still standing. The answer was inside the corona. The probe was inside the corona. And with each successive perihelion pass, the instruments were reading deeper into the physics of the most energetic sustained process in the solar system. The closest passes were still ahead. December 24, 2024. The Parker Solar Probe crossed inside 6.1 million kilometers from the solar surface, closer to a star than any object built by human hands had ever traveled. At that distance, the sun subtends an angle in the sky roughly 13 times wider than it appears from Earth. The solar disk does not look like a disk at all from that proximity. It fills the geometry of space in a way that no camera can fully represent, because no camera has ever been designed to operate from inside a star's atmosphere while simultaneously surviving and transmitting data. The Whisper imager captured what it could. The field sensors read the magnetic environment at 2 million samples per second. The Faraday cup on sweep glowed red at temperatures above 3,000 degrees Fahrenheit and continued to count ions. The probe was alive. It was measuring. And what surrounded it was the most energetically dense natural environment in the solar system outside the solar core itself. The solar wind at 6.1 million kilometers from the solar surface is not the solar wind that Earth's magnetosphere deflects. It has not yet become that. At this distance, the plasma has not had time to expand and thin into the relatively diffuse flow that fills the inner solar system. The particle densities are higher by orders of magnitude. The magnetic field strength is stronger by a factor that scales roughly with the inverse square of the distance, meaning that at 1/15 of Earth's distance from the Sun, the ambient magnetic field the probe passed through was hundreds of times stronger than what any previous spacecraft had measured in the near-Sun environment. The search coil magnetometer aboard the field's instrument suite, the component specifically designed to track rapid fluctuations in the magnetic field, was sampling at its maximum rate, capturing changes in field direction and magnitude occurring on timescales shorter than 1 millisecond. The data volume generated during a single perihelion pass at this distance exceeds the data volume from Parker's first 12 orbits combined. Not because the instruments changed. Because the environment itself became richer, denser, and more structured the closer the probe descended into it. Alphen waves, oscillations that propagate along magnetic field lines through a plasma in the way sound waves propagate through air, were present in extraordinary abundance. Alphen waves had been proposed since the 1940s as a mechanism for transferring energy from the convective zone of the sun's interior outward through the corona and into the solar wind. The Swedish physicist Hannes Alfvén, who gave his name to these waves after predicting their existence in 1942, was awarded the Nobel Prize in Physics in 1970. But the direct measurement of Alfvén waves in the solar corona, at the amplitudes and frequencies that would be required to account for coronal heating, remained observationally constrained only from a distance. Parker's instruments resolved that constraint. The waves were there. They were large amplitude. They were propagating outward along the open magnetic field lines of the corona. Their energy flux, the rate at which they were carrying energy outward per unit area, was measured directly by fields and sweeps simultaneously, allowing the calculation of actual wave power rather than inferred wave power. The numbers were consistent with theoretical predictions for Alfvén wave heating being a significant contributor to the coronal energy budget. not the sole contributor. Significant. The concept of Alfvén wave dissipation requires understanding one additional piece of plasma physics that is not intuitively obvious. A wave carrying energy through a medium does not automatically transfer that energy to the medium as heat. The wave must dissipate. It must somehow convert its organized oscillatory energy into the disordered thermal energy of the surrounding particles. In a plasma threaded by a magnetic field, this dissipation is not automatic. Alfvén waves can propagate enormous distances without losing their energy if the plasma conditions are right. The mechanism by which Alfvén waves finally dissipate their energy in the corona involves a process called turbulent cascade. When Alfvén waves traveling outward along a field line encounter Alfvén waves traveling inward, reflected from regions of the corona where the field geometry changes, the two wave trains interact. The interaction transfers energy from the large-scale, long-wavelength oscillations to progressively smaller and smaller scales, in exactly the same way that large eddies in a turbulent river break down into smaller eddies, which break down into still smaller ones, until the energy reaches scales small enough that viscosity converts it directly into heat. In a coronal plasma, the equivalent of viscosity operates through a process called phase mixing and ion cyclotron resonance, mechanisms by which small-scale wave energy couples directly to the thermal motion of individual protons and electrons. The waves, in effect, shake the particles until the organized shaking becomes random thermal motion. Temperature rises. Parker's measurements of wave power, turbulence spectra, and particle temperature distributions across multiple orbits allowed theorists to test cascade models with real boundary conditions for the first time. The turbulent spectrum measured by fields matched the predicted Kolmogorov-like cascade profile, energy distributed across scales in a specific mathematical ratio, with a precision that confirmed the basic cascade mechanism was operating as theorized. The heating was real. The mechanism was identifiable. The energy was flowing from the waves, through the turbulent cascade, into the plasma. The December 2024 perihelion pass also delivered the most detailed imaging of the solar corona's fine structure ever obtained. The WISPR images from this encounter, released publicly in July of 2025, revealed coronal structures at angular resolutions that no previous instrument had achieved from any platform. Coronal streamers, the long, blade-like extensions of solar plasma that extend outward from the sun and are visible during total solar eclipses, showed internal structure that had not been resolvable from Earth orbit. Fine-scale density variations, braided magnetic flux tubes, and narrow plasma jets erupting from the streamer belt were captured as distinct features rather than blurred aggregates. One class of features that appeared repeatedly in the WISPR data from close approaches was a phenomenon researchers called coronal jets. These are narrow, collimated streams of plasma launched abruptly outward from specific points on the solar surface, moving at velocities of hundreds of kilometers per second. They are distinct from coronal mass ejections, smaller in scale, shorter in duration, and more sharply bounded. Ground-based coronagraphs had observed coronal jets for decades. What Parker's proximity revealed was their relationship to the small-scale magnetic topology of the corona, specifically the connection between coronal jets and the mini-filament eruptions occurring at magnetic flux cancellation sites on the photosphere below. Flux cancellation occurs when a small bipolar magnetic feature on the solar surface, a tiny loop of magnetic field emerging from and returning to the photosphere, is transported by convective flows into contact with a region of opposite polarity field. The opposite polarities cancel each other through reconnection, releasing the energy stored in the field and launching a plasma jet upward into the corona. These events are small. Each individual cancellation involves magnetic flux far below the scale of a sunspot, but they are ubiquitous. The solar surface hosts thousands of flux cancellation events every hour. Parker's data, combined with the high-resolution surface imaging from Solar Orbiter, established that coronal jets, and potentially a significant fraction of the solar wind's mass flux, are driven by this continuous, distributed cancellation of small-scale magnetic features across the entire solar disk. The solar wind is not exclusively generated by a few large structures. It bleeds outward from countless small wounds across the entire surface of the sun, continuously and simultaneously. One of the most consequential data products from the December 2024 perihelion came from the ISIS Energetic Particle Suite. During the close pass, the probe measured the energy spectrum of solar energetic particles, the high-energy ions and electrons accelerated by solar events, at a location inside the corona where these particles had not yet had time to scatter significantly off magnetic field irregularities in the solar wind. The spectrum measured close to the Sun before scattering had altered it was sharper and harder than the spectrum measured at Earth orbit from the same events. Sharper meaning more particles at the highest energies, more tightly distributed around specific energy peaks. This had immediate implications for solar energetic particle forecasting, the branch of space weather science that attempts to predict radiation doses for astronauts and satellite electronics following major solar events. Current forecasting models predict particle fluences at Earth based on measurements taken at Earth orbit and extrapolated backward to infer conditions at the Sun. The Parker data showed that those extrapolations systematically underestimated the peak particle energies. The Sun was accelerating particles to higher energies faster than the models inferred from Earth distance measurements. For any future human mission beyond Earth's protective magnetosphere, to the Moon, to Mars, or to any point in interplanetary space, this matters directly. Solar energetic particle events are among the most significant acute radiation hazards in deep space. Underestimating their peak intensity by a factor derived from an incorrect scattering model is not a theoretical problem. It is an engineering and safety problem with direct consequences for mission design. Parker's measurements from inside the corona did not just advance solar physics, they refined the boundary conditions for human spaceflight planning in ways that no Earth orbit instrument could have provided. 6.1 million kilometers. The number is worth holding for a moment against the scale of the solar system. Earth is approximately 150 million kilometers from the Sun. The Parker Solar Probe's closest approach represents roughly 4% of that distance. Mercury, the innermost planet, orbits at approximately 58 million kilometers, nearly 10 times further from the Sun than Parker reached. At that distance, the probe's orbital velocity was approximately 635,000 kilometers per hour, approximately 176 kilometers per second. That is the fastest velocity ever achieved by a human-made object relative to the Sun. The speed of light is approximately 300,000 kilometers per second. Parker, at its fastest, was moving at approximately 0.059% of the speed of light. Not relativistic, not exotic physics, but the fastest thing humanity has ever built, screaming through the outer atmosphere of a star, measuring the fire from inside the fire. The heat shield's front face at that moment was absorbing approximately 23 times the solar irradiance that strikes the top of Earth's atmosphere. Behind it, at a distance of 4.5 inches, the instruments operated within their designed temperature range. The thermal engineering held, exactly as calculated, inside an environment that no engineer had been able to directly test before launch, because no test facility on Earth could reproduce those conditions simultaneously. The data stored in the probe's memory was transmitted back to Earth over the following weeks, at the rate of approximately 167 megabits per second during contact windows with NASA's Deep Space Network. The transmission took time. The analysis took months. Scientists at institutions across the United States, Europe, and Japan worked through data sets that contained more information about the near-Sun environment than all previous solar missions combined. Some of the answers were expected. The confirmation of magnetic reconnection, the presence of alpha waves at the amplitudes theory required, the structure of the solar wind close to its source. Some were not. The magnetic U-turns in the coronal mass ejection, the solar magnetic memory, the particle energies 1,000 times above the local budget. And some questions, sharpened by everything Parker revealed, remained open in ways they had not been open before. Not because the probe failed to answer them, but because the answers it provided were detailed enough to generate better questions. That is the specific way that fundamental science progresses, not through the elimination of mystery, but through its transformation into a finer, more precise, more honest form. The Sun is 4.5 billion years old. It has been doing this, burning hydrogen, driving its corona to temperatures that defy thermodynamic intuition, exhaling its atmosphere as a continuous wind that fills the solar system, for longer than the Earth has existed. Long before the first multicellular organisms appeared in the oceans of this planet, the solar wind was already sweeping past the location where Earth would eventually form. Long before the first hominids looked up and felt the warmth on their faces, the coronal heating problem was already operating, indifferent to whether anything would ever be built to measure it. The Parker Solar Probe was conceived in the early 1950s when the mathematical framework that would eventually justify its mission was still being written by a young physicist at the University of Chicago named Eugene Parker. It was formally proposed to NASA in the 1990s. It survived multiple rounds of funding reviews, technical descopes, and program cancellations over more than 2 decades of development. It launched on August 12, 2018. Between the first theoretical paper and the first perihelion data, 60 years passed. 60 years of accumulated knowledge, incremental instrumentation, and computational modeling. All of it aimed at a single region of space that no measurement had ever directly sampled. Science at this scale does not move quickly. It moves the way the solar wind moves through the outer solar system, steadily, continuously in one direction, accumulating distance without drama. What Parker confirmed, taken together across its 7 years of operation and more than 20 close passes of the Sun, is that the corona is not a single mechanism system. The coronal heating problem, framed for decades as a question in search of one answer, turned out to be a question with several answers operating simultaneously at different spatial scales, different time scales, and different locations within the coronal volume. Alpha wave dissipation through turbulent cascade is real and energetically significant, particularly in the open-field regions of coronal holes where the fast solar wind originates. The wave amplitudes Parker measured directly were large enough to carry the required energy flux when the cascade efficiency derived from the turbulent spectra was applied. That contribution is confirmed. Magnetic reconnection at current sheets, including the heliospheric current sheet and the small-scale current sheets threading the coronal loops of the closed-field regions, is also real, also energetically significant, and capable of accelerating particles to energies that affect both the thermal state of the corona and the population of energetic particles that escape into the solar wind. That contribution is confirmed. Magnetic island merging as a secondary particle acceleration process, producing the anomalously high energetic particle populations that Parker detected inside the reconnection exhaust regions, 1,000 times the energy predicted by single reconnection models, is real, observationally documented, and consistent with theory. That contribution is confirmed. Flux cancellation at the supergranule boundaries, driving the coronal jets and contributing a distributed component to the mass and energy flux of the solar wind across the entire solar disk, is real and spatially correlated with the switchback structures Parker observed in the near-Sun solar wind. That contribution is confirmed. The coronal heating problem is not solved. The precise partition of heating between all these mechanisms, the exact percentage contributed by waves versus reconnection versus nanoflares versus other processes not yet definitively identified, remains an open calculation. But the mechanisms themselves are no longer theoretical. They are measured. They are real. They are happening right now, at this moment, in the corona of the Sun, 3 minutes and 50 seconds of light travel time from the surface of the Earth. The space weather implications of Parker's data extend well beyond academic solar physics. The Sun is the dominant source of environmental hazard in the inner solar system, and that hazard is not uniformly distributed in time. During solar maximum, the peak of the Sun's 11-year activity cycle, the frequency of coronal mass ejections increases from roughly 1 per week to several per day. The energy released in a single major CME can exceed 10 billion megatons of TNT equivalent. When a CME of sufficient magnitude strikes Earth's magnetosphere, the geomagnetically induced currents it drives through the ground can exceed the design tolerances of electrical transformer infrastructure built before space weather was a recognized engineering consideration. The Carrington event of 1859, a solar superstorm that induced currents strong enough to set telegraph paper on fire and produce auroras visible at tropical latitudes, occurred before any of the infrastructure of modern civilization existed. A Carrington-class event striking the present-day electrical grid has been estimated, in studies commissioned by the U.S. National Academy of Sciences, to produce economic damages exceeding $2 trillion in the United States alone, with recovery timescales measured in years rather than weeks. Parker's improved characterization of the pre-eruption magnetic state of the corona, the magnetic memory effect that modifies the corona after each major CME, and the particle energy spectra produced at the eruption source rather than inferred from Earth distance measurements. All of these close gaps in the forecast models that space weather agencies worldwide use to issue warnings. The improvement is not marginal. It is structural. The models were built on incomplete inputs. Parker supplied inputs that did not previously exist. Dr. Angelos Vorlidis stated the practical consequence with precision. The magnetic field that returns to the sun after a CME changes the solar atmosphere enough that it can determine whether the next CME hits Mars or misses it entirely. That is the margin of difference between a catastrophic radiation event for a crewed Mars mission and a non-event, between a geomagnetic storm that trips circuit breakers across continental power grids and a storm that produces only a bright aurora. The data Parker collected is not abstract. It is navigational. It is protective. It belongs to the infrastructure of human survival in an increasingly space-dependent civilization. The probe itself, as of early 2026, continues to operate. Its primary mission phase, the 7 Venus flybys and the graduated approach to minimum perihelion, is complete. But the spacecraft remains functional, its instruments active, its data transmission ongoing during each subsequent perihelion pass at the minimum distance. Every additional orbit is science no one planned for. Every additional dataset refines constraints that existing models are still being rebuilt to accommodate. The Johns Hopkins University Applied Physics Laboratory, which built and operates the spacecraft, confirmed in December of 2024 that the probe's systems performed nominally through the closest approach. The same confirmation they had provided after every previous perihelion, 19 times before, each one a repetition of the same extraordinary fact. A spacecraft built to survive the corona survived the corona. Again, Eugene Parker, in the last years of his life, was asked in multiple interviews what it meant to him to have a spacecraft bearing his name fly into the region of space his equations had described 60 years earlier. His answers were consistent and characteristically restrained. He was interested in whether the data confirmed the models. He wanted to know if the solar wind was doing what his mathematics said it should do. The naming was incidental to him. The physics was the point. He was right about the solar wind. He was right about its existence, its structure, and its origin in the thermal expansion of the corona against the sun's gravity. The probe confirmed it from the inside, from within the solar atmosphere itself, at distances his 1958 paper could only describe with equations and no instrument had ever reached. Parker died in March of 2022. The probe had already completed 10 perihelion passes by that date. His work had already been confirmed in a way that left no room for alternative interpretation. He knew. The sun will burn for approximately another 5 billion years before it exhausts its hydrogen fuel and expands into a red giant, likely engulfing the inner planets, including Earth, in the process. 5 billion years. Against that timescale, the entire history of human civilization, every monument, every written language, every instrument ever launched into space, represents less than 1/1,000,000% of the sun's remaining lifetime. The corona will keep heating itself by mechanisms we now understand more clearly than any generation before us. The solar wind will keep flowing. The switchbacks will keep forming at the supergranule boundaries. The magnetic field will keep reconnecting at the current sheets, accelerating particles, heating plasma, driving a wind that sculpts the space environment of every world in this solar system. Understanding it more precisely does not diminish it. The opposite is true. Knowing that the corona's temperature defies the second law of thermodynamics, not because physics is wrong, but because there is an active energy input mechanism operating at scales from kilometers to millions of miles, confirmed by direct measurement from inside the corona itself, makes the sun more remarkable, not less. Proximity did not demystify it. It deepened the mystery in the best possible way, by replacing vague uncertainty with precise, measurable, testable questions. The fire is not smaller for being understood, it is larger. Because now we know, with the specificity that only direct measurement can provide, exactly how extraordinary it is to be close enough to a star to feel its warmth, and to ask, with instruments precise enough to receive an answer, how that warmth was made. The Parker Solar Probe did not touch the sun and find it ordinary. It touched the sun and found it stranger, more structured, more violent, and more beautiful than any model had predicted. That is the finding. That is enough.